Next, last speaker of this session is Dr. S. Robertson. Please come. So, already, she spoke a lot. What he's supposed to speak. Anyway, it doesn't matter. Dr. Robertson did his BSc from DM College of Science. He was gold medalist there. Then he went to Central University of Hyderabad. From there, he did his MSc and a PhD. Okay, he's associating with us in the research. Okay, together. So he did in B physics, CP violation, in PhD, now in neutrino physics, and now he is teaching in Wharton College. Okay, so please continue.
Thank you, sir. Yeah, good evening, everyone. Actually, what I'm going to speak is already spoken by many experts here, including, the most recent one was spoken by Gomti ma'am. So, and many things was also supported by Nimaisha. So, I will be doing some recap of what we learned in this workshop. Yeah, so what we are going to see in this presentation is some topic on origin of quantum mechanics, then Schrödinger wave mechanics, Klein-Gordon equation, Dirac equation, and the hydrogen atom energy levels that ma'am already spoken very nicely. Yeah. So quantum mechanics, actually this part of quantum mechanics we call as all quantum mechanics. So the first idea of quantum mechanics comes from the Planck's explanation of black body radiation by giving the equation E is equal to h nu, and Einstein used this equation to explain photoelectric effect, and this is the equation of work function where h nu is equal to work function plus kinetic energy of the electron. And Bohr explained the spectra of hydrogen by quantizing angular momentum, and our angular momentum cannot take all values, but it must take some particular values, and that values must be proportional to h by 2s pi. And from here we have new quantum mechanics, and we call new quantum mechanics as simply quantum mechanics. And for that we have matrix mechanics formulated by Heisenberg, and wave mechanics formulated by Schrödinger. And for matrix mechanics, Heisenberg formulated that our observables must be the eigenvalues of operators, and the time evolution of the system is governed by our Heisenberg equation. And for Schrödinger equation, we have I think most of the faculties and most of the students here already know this equation. This is our Schrödinger equation, where the Hamiltonian takes the form like this. And here our Hamiltonian has kinetic energy part and the potential part, and by Schrödinger equation our Hamiltonian must be an operator, and if it is an operator, then it is meaningful to act on a state, and we call this as a wave function. And the wave function itself doesn't have any meaning, but what we can get from the wave function is the probability density. And this probability density, as we can see from the expression, this is the modulus square, so it is always positive. Yeah. Sorry, this is the Klein-Gordon equation, and for the Klein-Gordon equation is based on this sorry. Yeah.
So we have come to the wave mechanics. Now, Heisenberg's matrix mechanics.
Yeah.
What led him to consider matrices as the mathematical identity to define this quantum mechanical world? Any idea?
According to my knowledge, Heisenberg was interested in observables, means the value, the final end region, not the wave function. He didn't means he didn't understand, or maybe he didn't want to go to this wave function that is not observable. So if we we can express that in terms of matrix mechanics, then
the reason why I ask is
yeah.
that it seems Heisenberg himself was not aware of what is a matrix, what matrix is.
Okay.
So he had the idea, then he later on discussed with Jordan,
Okay.
and that's what actually gave rise to it.
Yeah. I didn't know. Thank you, sir.
But another thing is, let us take that. Another thing what I learned from someone is that Schrödinger equation will give the physics of one orbit. Heisenberg says that the meaning of one orbit has no meaning. When there is two orbits, when there is something transit, only then it is measurable. One orbit has no meaning. When there are two orbits, the difference is measurable. So Heisenberg equation try to give the differences.
Yes.
Jumping from one orbit to another.
So we get observables at last. Observables. So
Relation between the observers.
yeah, observables. So if the eigenvalues are the observables, then we can get more than one values, and we can find. So Klein-Gordon equation is based on our relativistic equation, and like before, we got our Schrödinger equation by putting the form of operator for energy as this, and for the momentum as this. And if we put this form of operator, then we can very easily get this equation. And this is our Klein-Gordon equation. And if we calculate the probability from the above equation, we will get this formula. And for a plane wave solution, if we put aside this, then we get our probability depends on the energy. So the energy from here is set. This energy, our energy is E square is equal to P square C square plus M square C to the power 4. So if we want to get the energy, then we will take square root of this function, and we will get plus and the minus sign here. So that means we can have negative energy. For the negative energy, from this formula we can see that the probability is negative. So Dirac was Nimaisha already mentioned that Dirac want to have a positive probability equation. So Dirac showed a first order differential equation to avoid this issue. For that, Dirac's aim was to have the equation of this form, where both the time derivatives and our Hamiltonians are first order. So, but this Hamiltonian must also satisfy our relativistic relation. So Dirac took the form of the Hamiltonian like this, and here we have C alpha is a here I could say a number, but there will be a matrix. But here alpha dot p plus beta mc square, and here I have written here that alpha and beta are matrices, and this Hamiltonian must satisfy our relativistic relation. If we put the form of Hamiltonian, like we have mentioned in our previous slide, then this is the Dirac equation. And this Dirac equation, since we want to satisfy this particular formula, we got some condition on our matrix, or I can say number, and then let me explain that this can be a number here. From here we can see that we have alpha I beta plus beta I alpha is 0, and this relation cannot be satisfied by a number. So this, in order to satisfy this relation by a satisfy this equation, we must say that these are not numbers but rather matrices. So
And by the way,
Yeah.
Bharat was not a physicist by training. He was an engineer.
Yes, yes.
yeah.
He is engineer.
So it's
Yes,
amazing that
yes.
He formulated this. Maybe he did so because he was not biased by all the.
Yeah, yes, sir. But this equation, we can see that this cannot be a number.
But then at that point of time, yes, now it is obvious, but those days,
Yes.
there was a time when matrices were not so widely used.
Oh, okay. Yes. But but this relation cannot be satisfied by a number. Yeah. Yeah. This. Yes. So we can get our here. I just wrote that the probability density rho is positive, but it is I haven't written here. But if I wrote, we can see.
P by MC square beside
What?
Yes, right.
Yeah, yeah. Ah.
Please continue.
Okay. So energy solution for Dirac equation is like this, and from here also we can see that we can get negative values, and these negative values is unphysical in our classical interpretation, and this is and Dirac tried to explain the negative states as the vacuum, and the vacuum or a Dirac sea is completely filled by the negative states. So if there is completely filled, then by Pauli exclusion principle, an electron cannot jump down to the Dirac sea, since it is completely filled. So he could take only the positive energy states. And if we want to excite the negative energy state, then we could arrive a hole and an electron, and we could create our electron and the positron, and that hole we now know as positron. And this for energy, I just wrote the expression for hydrogen atom, energy of hydrogen atom, and from here we can see that our energy depends only on our principal quantum number n. And for Dirac, we can see that it depends on principal quantum number and the total quantum number j. So if I have time.
That doesn't matter. Continue. No problem.
I whiteboard on I
Okay.
sorry.
So I should not use my test, huh?
I think ma'am already extend this concept, but since I have included in my slides, so I will explain.
You are introducing thumb symbol.
Yeah.
That is better.
So for the thumb symbol, we have this L, which is our orbital quantum number, and the J here is our total quantum number, and this is the spin quantum number. And for n is equal to 1, the L can be 0, and the S is 1 here. So what will be our capital L is actually our L1 plus L2, but since we have only L here, so we should take L is equal to J here, 0. And the S, capital S is S1 plus S2, but since we are considering hydrogen atom, so it will have only one value, which is half. For finding J is L plus S here. So let me write like this. If we have a angular, if we want to add to angular momentum, then the possible value it can take by this by this is J1 plus J2, then J1 plus J2 minus 1, and it goes till it becomes negative. So for this, since we have, yeah, it cannot be negative. Stop at means before negative.
How about J minus 1? J minus 1, J2.
No, it can be. I told means it. We should stop before it goes to negative. Up to 0. It can take up to 0.
It need not be 0.
Yeah, it need no. Yeah. If it may not be 0 also. Yeah. From this example, we can see that it is not 0. So since L is 0, S is half. This will be half, and the half minus 1 is minus half. Since minus half is negative number, we can't take that value. So for n is equal to 1, J is half, and this can be written as, since we are having L.
Up to 0 what's a pair J1 में J2 के दो.
0 सत्य सर.
And then minus 1 or didn't check it in 0. J1 plus J2.
I get techniques na sir. Toroga stop to have 0 setting it. Asing budis mai I gada ne sir. Is the slide for the E.
Triangular inequality.
LS coupling tawdorira, JJ coupling tawdorira.
LS. Asing budis mai gada. I get understanding the. Asing budis is sir. We should take modulus. Modulus slow. I not over the cannot toroga. I cannot. So this is, since this is L is equal to 0, S, and our J is half here, and the 2S is 2 here, and you want to put here 1. I think I will just write for n is equal to 2, and here L can take values 0 and the 1, and the S can take values half. For J is equal to, for L is equal to 0, we can calculate J, which is L plus S, and it can, now here we can take half, and for L is equal to 1, is equal to half, it can take value 3 by 2 and a half. Like this, we can get the different. So this can be represented 2s half, and this is our 2p 3 by 2 and the 2p half.
better, you get SPB.
Yeah. Yeah. So I will just stop here. So for n is equal to 1, we can get only one value of j, which is half. So this is 1s half, and for n is equal to 2, previously by Schrodinger equation there are all degenerate states, but according to the Dirac, now since our energy values depend on n and the j, so we have the splitting of energy levels. Here this is different j, so it will split from the same j. But our Dirac equation does not depend on the value of L, so both even though they have different value of L, they stays in the same level. And here also we can see, according to Dirac equation, they are degenerate, but from here we have three energy levels, one for the 5-2, another for 3/2, and lastly for half. Yeah, from here we can explain our fine spectral lines, and that could not be explained by our Schrodinger equation. Yeah, that is the last slide, that Schrodinger equation is non-relativistic and Dirac is relativistic, and the sir already told that if we put a potential or interaction in the Dirac equation, we could not get our Lorentz invariant, and so it's not purely relativistic.
Very good.
Yeah, thank you.
Any question? I think in between we have discussed. Anybody? Yes. So, for you, I class it out to the.
2/2 na this is satisfied over number relation, fast relation though.
2/2 the.
It must be even, maybe 4 and other even numbers.
2/2 are Pauli matrices. Okay, there are only 3 independent 2/2 Pauli matrices, not 4. Dirac equation need 4 independent matrices. Therefore, 2/2 is out. 3/3 is Dirac matrices should be square matrix. It should be n cross n. Okay, but 3/3 is not allowed. 3/3 matrix is not allowed. Okay, the proof story. Third, the only left is 4/4 matrix. And then masang gati. More
Sorry.
Oh. No. So in the equation, the Pauli na put the kun ama that is not allowed. We want to come out from the equation.
My Robertson
Yeah, Dirac, if you want to explain, they explain to the Havata, the Schrodinger equation, I couldn't happen the Iva, couldn't happen to the Aquapam deal. Okay, Pam is equation Masama take it Hokter of Neva. A dugi example of my Havata Ragadi, a question the River Sidala River, Sigi matrices form say, Sida and Dum Aquana express almost on the Pauli matrices and Dum Yauzara Caneva. A didna spin and Dum explain to Bangamev.
I can come in number one, this is a very important things for us in quantum mechanics. I want to say is that Einstein is not honest. Einstein is not honest, and even though he developed special theory of relativity, general theory of relativity is but he knew that when his equation is taking square root, there should be minus sign. He kept silent. He was not stupid. He knew that there will be minus sign. Dirac is very honest person. He could not hide the mathematics. He was worried about the negative sign, negative t. But Einstein, even though the equation was developed by him, he hid the things, the issue. That is one comment from me. I don't know, I may be wrong. But anyway, Einstein is also right, because in classical mechanics, this minus sign These are not so important. In quantum, it is very important. This is number one. Second point, Dirac equation without, in the presence of electronegative equation, there is no spin term. Spin terms will come only when either hydrogen atom or in the presence of electromagnetic. So he is a good man or bad man, nobody knows. Only when he is disturbed by someone, he show his hidden qualities, whether very ferocious or very thing. Like that, when Dirac equation is put in electromagnetic field, the spin is the magnetic field. The magnetic field of the spin and the outside magnetic field will interact. This is how the extra term will come, that is your mu. That gyromagnetic ratio will come only when Dirac equation is put in the external magnetic field, because two magnetic field will interact. The magnetic field created by the spin and the outside magnetic field. This must be very clear. The second point is he also pointed out that how do you know that there is a Dirac equation can explain there two ways. One is electromagnetic field, and second is she's zero way there. She never zero way.
Conservation of total
These
angular.
two will show that Dirac equation is okay.
I don't know JJ small JJ complete small l small s complete.
There is one thing I read one Russian book. When you jump into the river pond, Brahmaputra river or in the Imphal Torrent river, when you open your eyes, can you see the drop of water? Can you see the drop of water? When you jump inside the water, can you see the drop of water? Anyway, no. Why? Because the continuum. In Dirac equation, C is continuum. There is what called continuum. Don't forget. Continuum. Dirac C is continuum. Dirac C is continuum. Continuum means there is no gap. There is inside the water. When you open the eye inside the water in the continuum, I cannot see the drop of water. When drop of water is isolated only, I can see the drop of water. Aduna, we cannot measure the negative energy electron because they exist inside the continuum. In order to measure the negative energy electron, we have to isolate. Aduna cinema kita, Amitabh Bachchan angang bagal atopa na masu karlela jagoi sai. He wants to be isolated from the continuum. The third point that Dirac equation ki amaru orisi koi ki hamoina the probe cannot see the ant. If the ant is at rest, the probe cannot see. When the ant is trying to move, the probe jump to this and he can see. Just like dinosaurs. When the dinosaurs come, if you like the dinosaurs cannot see. Like that, the some compound eyes, simple eyes, I don't know in biology, there is some difference. Because the probe eyes cannot identify the ant from the surrounding. Only when it moves, he can see, the probe can see. So this is what about the negative energy. People ask that why we cannot measure negative energy, because they are inside the continuum. So please don't forget the word continuum Dirac. Otherwise there is no meaning. Okay, thank you.
Sir. Thank you, sir.
So let us give the Okay.
Thank you, sir.
Okay. Okay. Okay.